Okay, so we started with the problem, x of t equals 4t, y of t equals 6t squared. So what's y of x? Okay, well, the general way to express y in terms of x, when x and y are both in terms of a parameter t, is solve for t. Uh, and then substitute. So we're trying to get y as a function of x. So we're going to be able to say that t is x of t over 4. Very obviously, you don't have to do the steps of that. Y of t equals y of x over 4. I should have just said y equals x over 4. Equals 6 times x over 4 quantity squared, which is 6x squared over 9. No, wait. 16. So y equals 3/8 x squared, 3x squared over 8. Now, make sure I did that right. Some people did a little bit of strange stuff on the picture. I did do something wrong here. I think I'd see some people getting a 96 here. I think it's pretty straightforward. If x is 4t, t is x over 4, and you plug t in here, you get 6 times x over 4 quantity squared. I think this is it, but let's make sure. Okay, there's another way to do this. The differentials. What's the differential? What's dx? And what's dy equal to? Well, dx is just a differential. If you don't remember differentials, you really need to know differentials. It's one of the fundamental things in calculus. We use it all the time in differential equations. We took that course. Okay, so we got dx equals 4 dt and dy equals 12t dt. So that dy over dx equals 4 dt over 12t dt, which is 1 over 3t. Now here we find that dy dx is 3/4 x. If t equals x over 4, And something screwy here. I must have done something wrong. Getting 4x over 3 here. Well, main reason I do this is to show that you can manipulate these things as differentials. And got a comment here, and somebody's probably seen what kind of bonehead thing I did. So that didn't come. All right. Okay. It was politely pointed out, hey, bonehead, you put the dx over the dy. Okay. So if I do it right, we'll just the dy is okay. So just to be careful, that's 3x squared over 8 multiplied by 4. It's 3/4 of x. The x that looked like it was in the denominator. It's 4x over 3. That can't be right. The x does have to be in the denominator. Where in the world is it? Okay. Yeah, and that's 4 over 3x. It's 3x is your numerator. Okay. Which is then, still doesn't work out. What am I doing? Obviously, what I'm doing is not arithmetic, because I apparently can't do arithmetic. Okay, I went back to here. Now I'm substituting the wrong stuff in the wrong place. dy is 12t. Dx is 4. It's 12t dt, and it's 4 dt. And now it's 3t. And if t equals x over 4, dy dx equals 3 times x over 4, which is 3/4 x, which is what I was trying to show, right? Okay. All right. Sorry for the confusion. More that you can say about this. First of all, a graph of y versus x is just going to be a parabola. Parabola 6x squared over 16, which kind of looks like this. Okay. And if you want to put a scale on it, if x equals 4, y equals 6. So let's see, if here's x equals 4. Here's y equals 6. We don't have equal scales here. 4 on the x-axis is bigger than 6 on the y-axis. So the scales kind of compress. If we well, there it is. Okay. If I was to make a table, take a few times like 0, since we're squaring t, let's let t be 0, 1/2, 1, 2. Then x is going to be 0, 2, 4. Let's do 3/2, then 2, 6, 8. And y is going to be 6t squared, which is going to be 0. 1/2 squared is 1/4, so it's going to be 3/2. 1 squared, of course, is going to give us 6. 3/2 squared is 9/4. 9/4 is 6, is 1/2 times 6, that's like 13.5. And at 2, you're going to have 24. Okay, so the t equals 0 point is here. The t equals 1/2 point is at 2 3/2. So let's see, do a line for x equals 2 and y equals 3/2. Be about there. Then 4 6, which we already had. Then 6 13.5. And eight up here somewhere. Here's t equals 2, t equals 3/2, t equals 1, t equals 1/2. So if t is interpreted as time, you see that we're moving along this curve, changing direction, and speeding up, right? So what's the average rate of change of y with respect to x between t equals 0 and t equals 1? Jot it down. I'm just gonna look over your shoulder and see if everybody's getting it. Just to see how much I gotta say to explain it. Won't take a minute to digest. Okay, I'll go ahead and just fill this in because people are still kind of digesting it. Change is delta y over delta x, the average rate of change. That's the most fundamental definition in calculus. You take its instantaneous limit, and you have the derivative, and you're off to the races. Okay, you got to be sure you understand that. So make sure you understand that little connection. But the delta y is 6. And the delta x is 1. At t equals 0, you're here. At t equals 1, you're here. You change 1 unit in the x direction. Whoa, wait. Delta y over delta x. I'm sorry. I was doing delta y over delta t. 6 over 4. Okay. So from here to here, your average rate of change, of course, is the slope of this secant line here. Okay. And it's 4 units this way, 6 units this way. That's 3 halves. Okay. Now, what's the instantaneous rate of change at x equals 2? Yeah, x equals 2. And of course, x equals 2 is halfway between 0 and 4, right? Well, I'm going to give you a quick answer, let you process it for a second, but it's just dy dx is 3/4 x. Just talk about derivative here, right? That's the instantaneous rate of change of y with respect to x. Well, if x equals 2, dy dx, just plug in 2 for x, you get 6/4, which is 3 halves. So your tangent line here do that in a different color. Hard to write with this chalk. That's supposed to be the point 2, 3 halves. I can't get the 2 to come out. If I try to erase it, it'll smudge. But you know what that point is. Okay? Now, does that make sense? Everything kind of hang together to make sense? Well, there's another thing we can say is that dy is 12t dt. Okay? If t equals 2, then dy equals 24. And if x equals 2, that's just 4. 24 over 4 isn't 6. So that connection I was going to make here, for some reason, it isn't working, and I don't have to make it right now because I want to skip to something else anyway. Okay, something's a little bit screwy there because if I do dy over dx, I do get 3/4 x. And if x is 2, that equals 3 halves. But if x equals 2, dy is 12 and dx is 4. And dy dx is 3t, and 3 times 2 well, that's in terms of t. It's 3t. T is 1/2. Okay. I was using x instead of t because apparently my brain isn't totally focused right now. I apologize for that. Okay, so again, at this point, we're looking at t. T is 1/2, and this is dy dx in terms of t. So t is 1/2, so dy is 12 times 1/2 times dt, which is 6 dt. and this is four dt. 6 dt over four dt is 3/2 dt, or 3/2 t, which is 3/2. Okay. And consistent with this. Everything's consistent, and that's nice. Now let's make a little bit more sense out of this, because what we really want to do is model motion along this curve. That's why I've indicated T at all these points. The motion along the curve is such that what's your speed at this point? Well, that's a little bit complicated. Okay. You could say that between here and here, we moved a distance equal to the hypotenuse of a triangle with base 4 and altitude 6, right? And that would be square root of 36 and 16, which is 52. Okay, square root of 52, a little over 7 units here. So we're moving a little over 7 units per second on the average between here and here. Does that make sense? Okay, because it is a little over 7 units at your distance. Your actual speed at this point is going to be square root of dx squared plus dy squared. Then I'm going to develop that. If you do at t equals 1/2, dy is 6 dt, dx is 4 dt. So you do 6 dt squared plus 4 dt squared, you get 52 dt. So that turns out it should be right. But yeah. Okay, well, let's put this into something coherent. I'm not sure I want to get rid of this, so I think I'm going to do it like this. Now, how much board can I see from there? This much. Okay, so I can use this. All right, now here's our picture. I'm going to define a vector function. Four t times the I vector plus 6t squared times the j vector. Okay. And I'm going to plot that vector function at t equals 0. When t equals 0, I get 0. Well, let's just go ahead and do a table. T R of t. When t is 0, R of t is 0, but it's a 0 vector. When t is 1/2, R of t is 4 times 1/2 times I, which is 2I, plus 6 times 1/2 squared is 6 times 1/4, or 3/2. Okay. So let's see, I can start with the 0 vector, which I'll just indicate with an X here. The 2I plus 3j vector. Is right here. T equals 1, I get 4I plus 6j. And that vector, if you do the arctangent of the y over the x, is going to have a little bigger angle than this one. And it's going to be a good bit longer. Maybe it's here. Not going to try to be real accurate. Consider this kind of a semi-schematic. Get 3/2. We plug in 3/2, we get 6I. plus, I want to do it. Something wrong with my previous calculation. 3/2 squared is 9/4. That'd be 9/4 times 3/2. Still 13.5 J. And when T equals 2, we're at 8 I plus 24 J. That table is very easy to make. Again, this is not totally accurate, but six I plus 13.5 J. Should probably be a little longer than that. Put you at this point, and then 8 I plus 24 J. I'm going to erase that because I want to label this one on this side, and then this one up here somewhere is your 8 I plus 24 J. Now these points can be connected by a smooth curve, and lo and behold, you have the same parabola that we had over here when we graphed the function. Okay. Three x squared over 8 function. But now we think of motion along this path. And again, this is T equals 0. Here's the point where T equals 1. So that's 1/2. T equals 1 point is here. T equals 2 points up here. T equals 3/2 points here. I'm not going to label it. Now that we have this vector function, we calculate its derivative. So calculate the derivative of dr dt. Very simple derivative. Okay, again, I went into an anecdote about a professor who was an NFL quarterback and advised us, and it's an advanced undergraduate course, advised us to not write a bunch of stuff down because it's all there in the book. He's just presenting it and commenting on it, but to follow what he's saying. I wasn't real good at following what people said. I was better at reading it, but it was in the book. So I eventually got it reasonably well. Okay, so anyhow, oh yeah, and when I asked what my final grade was, he said 72. I said, oh geez, maybe I will change from physics into mathematics. He said, I'm not sure it merits that. I did anyway, and kind of did okay with it. Okay, well anyhow, speed is what? You got the vector position. How is speed related to position? It's the rate of change of position with respect to time, right? So speed is but it's not the rate of change. It's the absolute value of the rate of change because speed doesn't have a direction. It's the magnitude of the rate of change. So And by the Pythagorean theorem, that's the square root of wait a minute. Yeah, that's right. Okay, after out the four, you get 4 times the square root of 1 plus 9. But the main thing is, it's this component squared plus this component squared, you take the square root. It should be obvious why that works. Okay. What's velocity? Velocity is just dr dt. And you could also say speed is the magnitude of this, which is what we already did. Okay. What's the acceleration? Write it down. Very simple. Okay, can you calculate it? It's exactly right. Exactly how you want to start. That's right. Yeah, just do it. Okay. Acceleration is the rate of change in velocity, which is the instantaneous accelerations, the instantaneous velocity, which is just 12J. Now, if we look at the graph, we can see aspects of this. First of all, our velocity, well, there's no acceleration in the x direction. All the accelerations in the y direction. All the accelerations are multiple of j, which means that at equal times, we should be moving equal distances in the x direction. Well, this picture is a little messy to point at, but this is the same picture essentially. And we see that we got x equals 2, x equals 4, x equals 6, and x equals 8 at time intervals of 1/2 second, uniform time intervals. So motion in the x direction is constant, like a projectile if you've had physics, an ideal projectile, okay? And the y motion is uniformly accelerated, uniform acceleration of 12 acceleration units in the y direction. Okay, that's kind of a good thing. And if you've had physics, you can relate that to projectiles. If I had made y of t negative 6t squared, then it would be a downward acceleration. Okay. And the downward acceleration would be 12 units because, well, I'm not going to go to there. Just because that 1/2 you get when you integrate t. Okay. So this gives us a general picture. Just a specific example of a general picture that's fairly easy to understand. The operations are easy enough. They're just simple calculus with very simple functions. Okay, functions aren't always that simple, but a lot of times there are sines and cosines. So now we have a picture of some sort of path in space. Doesn't have to be a function, you know, things move forward and backward in both directions, right? Let's just say that's some sort of path that's defined by some function. R of t equal x of ti plus y of tj. Then you just take the derivative with respect to t, and you have the velocity. Acceleration is second derivative of r with respect to t, which is, of course, derivative of velocity with respect to t, which is x double prime of t I plus y double prime of t times the j vector, and that's getting a little sloppy. It's still on the board, miraculously. So that's all, you know, very straightforward. But it doesn't stay straightforward. It's not that bad. I'm going to give you the picture. This picture skips a couple of sections ahead of where you're going to have the assignment. But I think, in my experience, you can do that. Okay. Because the overall picture is pretty simple. And I'm anticipating the possibility that we're going to miss our next class. At best, we're going to be on snow schedule, which doesn't make that much difference except in the duration of the class at this hour, but it's a little later. Because it's going to be down in zero range on Monday night. People won't be able to start their cars, won't know enough to put on coats, and they'll freeze to death and sue us. You know, that's sort of stuff. Maybe they don't have a coat, you know. In that case, you probably don't want to be out in zero weather, do you? So anyhow, it's going to be warmer than that by this time, but. Okay, so anyhow, you have your acceleration function. I should have written a of t, but that's implicit. The speed. Is the magnitude of the velocity, which is the square root of x prime squared plus y prime squared. And I mean, often written, your book will probably use dx dt squared, dy dt quantity squared. I'll use the prime because it's quicker and more compact with the same meaning. Okay. I don't think that'll be a notational problem for you. Okay, so what if I want to find how far I move along this curve? How do you put speed together with time to get how far you go? Okay, now I talked to people and tried to talk them into something. And the conversation went something like this. Okay, if you know speed and time, how do you get the distance? And so, well, you speed is distance divided by time, so you multiply the time by the speed. And that's true if you have a constant speed. But what if you don't have a constant speed? Somebody piped up and said, you just use the arc length formula, it's kind of up there. Well, it's part of it right there. No, 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 you don't use the arc length formula just yet. You don't really need the arc length formula. All you need to do is understand what I've written here and how you get distance if you know speed. If the speed is variable, you can't multiply the speed by the time, okay, by their time interval, okay? You can't do that because you have different speeds. Which speed are you going to use? Well, you could use the average speed. How are you going to get the average speed? Okay. Well, finally, after I gave somebody a hard time about the arc length interval, and it was a good answer. But the idea here is understand it before you use it. And then use it and understand it better and better as you use it. But keep thinking about what the heck it means, so you don't forget it. If you forget that formula and don't know what it means, you'll never get it back. You're on a test under pressure, or you're trying to think through an engineering situation, and you don't want to have to go look up a bunch of formulas. AI is going to do that. You have to think. Okay? Okay, so finally somebody said you integrate the speed with respect to time. Yeah, that's how you get distance. So it's the integral of speed with respect to time from like T1 to T2. Written a little small, but it's an obvious integral. And that equals the integral wrote it kind of small, x prime squared plus y prime squared dt from T1 to T2 equals, written out in a little more standard form that's very useful. Instead of x prime squared, you do dx dt squared. And there it is. And that's your standard arc length integral, but all it means is speed is a function of time. And if you know your position function is a function of time, you do a couple of derivatives, you get the velocity and the acceleration, you take the magnitude of the velocity, and there it is. Make sense? So try to understand it at that level, because that's a level at which you can think about it. You get the right answer, but calculators have been able to get the right answer for decades. Getting the right answer doesn't mean you know how to think about it and know how to apply it. Okay? Very important. I think it's very important. I think it's even more important with AI out there, because if you can't add thoughts to AI, you're going to have a shaky career. Okay? So develop those thinking skills as best you can. And they're good even outside of your career. It's good to be able to think clearly and deeply. All right. Next obvious thing to do is, what's my direction at time t? Actually, come on out here. Okay. Now, let's make sure we understand how this R thing works. Here's R of t vector. And here's my point on the curve. The R of t vector is rooted at the origin. It just moves around, tracing out your curve. Okay? So what's my direction right here? How am I going to calculate just my direction? Okay, people want to do bizarre things with this thing, but it's interesting. Okay, and don't feel bad. I told you, I really knocked the top off of this course at a really tough school, okay? And I don't think I could have answered that question if I was in this class at this point. It would have been very obvious to me very quickly when I saw the answer, and I think will be in year two. So people are saying, use the components. I say, use the components of what? Use the components of the R vector. Okay. Well, these are the components of the R vector. What's your direction at this point? It's this way, right? So these components have nothing to do with this. And then the angle of the R vector with the x-axis. Well, that's this angle, which again has nothing to do with this direction. Okay. So I kept pulling. And I think we finally got around to the idea it's the velocity vector, because the velocity vector has a magnitude and a direction, and the direction is the direction of motion. Okay, so you got to get the direction of the velocity vector, which would be the arctangent of y prime over x prime. That's fine. I want to get a vector in that direction. Well, I've got one. I've got the velocity vector, right? It's a vector in that direction. Okay. Now, come back to that in a minute. I also made some comments that I think are kind of interest. If you're trying to use the R vector, just the R vector and the components of the R vector, anything at all about the R vector, except the derivatives, the curve is where it is. The coordinate system could be, the origin could be anywhere, so the R vector could have any old angle. Okay? Coordinate system could even be rotated. It's not hard to rotate a coordinate system. We'll do that, I think, in linear algebra too. You have rotation matrices. Sine, cosine, negative cosine, sine, all that stuff. Okay. All those transformations are linear transformations. What happens to linear stuff when you take the derivatives? Derivative of anything that's constant and its constant linear coefficients is zero. So they all go away when you do this. It doesn't matter what the direction of your coordinate system is. It doesn't matter where the origin is. Relative to your coordinate system, you're going to you have a vector here that's tangent to the curve that's in your direction of motion. Okay? So, not R, but the velocity, which is R prime. Okay? Okay. Well, now we're close to something that's really pretty cool. You want to get a unit vector in that direction. How do you get a unit vector in the direction of motion? Okay, not surprisingly, I got an answer fairly quickly because, of course, the unit vectors were part of the homework you did for today. Okay. So when I say, let's get a unit vector in the direction of motion, spelling it out. The unit vector in the direction of motion is the unit vector in the direction of your velocity or your r prime, your dr dt. And it doesn't matter if you're talking about time or some other parameter. Okay, you use arc length as a parameter. You'll see about that. You use any parameter. When you take the derivative of r with respect to whatever your parameter is, t, s, or aardvark, you're going to get a vector tangent to the curve. And if you take a unit vector in that direction, it's r prime over its magnitude, or if you prefer, d prime over its magnitude. Fair enough? And t is your unit tangent vector. Okay, now we don't have a whole lot of time, but I want to try to get one more idea into your head. This is where we're leading, and it's not very complicated, except where it gets complicated. It's a little more complicated. Okay, you have an acceleration vector. Now, what's an acceleration vector? Let's say you're driving around a circular track. What's the direction of your acceleration? If you're driving at a constant speed, your acceleration is centripetal toward the center. You're not changing speed, so you're not changing your velocity in the forward or backward direction, right? Your speed is staying the same, so you're not speeding up or slowing down. But to stay in the circle, if you're a Newtonian object, you're moving in a straight line, and there's no force on you, right? Okay, constant speed, straight line, no force. In order to move in a circle, you need a force pushing you in. Which is why your tires wear out, which is why you blow this knee out if you try to turn too fast that way, which I did once. It hurt. There's a medial ligament. It healed. Didn't have to have surgery or anything. Slowed me down for a while though. And no, it wasn't that fascinating, so there's no big deal. It was out here playing intramural football. I think I wore shoes that day, which is a mistake. Out there were the higher education centers, there's football field. Go out there and play for a couple hours every Tuesday and Thursday. And I think my Rick Hatfield cut back on me. I planted this foot and the cleats grabbed too hard and that knee just went. Yeah. So, the intense pain only lasts about 30 seconds and that got tolerable. No big deal, but you want to avoid it. Okay, now point is, that's because I needed a centripetal acceleration to curve my path around to catch him, which I wasn't going to do anyway. He was too quick for me. Okay. So if I'm moving here, depending on how fast I'm moving at a constant speed along this, where am I going to have the greatest centripetal acceleration? Well, it's going to be where I make the sharpest turn, which is right about here. Okay, what's the direction of the centripetal acceleration? It's toward the center of the osculating circle. Everybody has to see the osculating circle. It's just a circle that matches this curve for a short time. Actually, an infinitesimally short time. It's kind of a circle tangent to the curve. It's on the inside of the curve. So here is centripetal acceleration, which I call the acceleration perpendicular to the curve. Okay. Now I might also be speeding up at this point or slowing down. So I could have a tangential acceleration. I'd label these, but we're out of time and it takes time, but so you just kind of understand. I'll label them when I'm done, so they'll be there on the video. Okay. The net acceleration is the vector sum of these two, which is just, these are perpendicular to each other. So here is good old A of t here. Now, the only thing left to understand this is figuring out the radius of the osculating circle, then figuring out where the center is, and you get the equation of the osculating circle, which is very interesting. Now, if you're in 3 dimensions, you also get pitch, you get yaw, and stuff like that. But it's no harder to do 50 dimensions than it is 2 dimensions. Just add vectors. Only 3 dimensions of space. There are lots of things that you want to, data science deals with millions of dimensions. And the topology and shapes of things in millions of dimensions, which is real tough. I don't know much about it either. Okay, well, there it is. There's kind of a overall pretty good picture and overview of motion. And it can apply to 3 dimensions as well as 2. If you've got a k component, then you have z of p times k, and you just take derivatives, whatever you got, and you get a velocity vector in 3 dimensions. Get a rate of change of velocity, the acceleration, and all that stuff. Make sense? Okay. I'll just mention that to get this component of acceleration. No, never mind. I'm not going to say it. I might say it wrong. Okay. Y'all have a good weekend. Hopefully we don't get snowed in or iced in, which is worse. But we're probably going to at least be meeting late on Tuesday. I'll put an assignment up on the assignments page. Does everybody know where that is?
The syllabus.
Okay, promise to label these 2 things. This is a centripetal acceleration. It's perpendicular to the path. Here's the tangential component of the acceleration. It's parallel to the path. Here is your resultant acceleration. Has a component parallel, component perpendicular to the path, so it's in this direction.